double angle identity here. So up here at the top, we have got sine of 2 theta equals sine theta cosine theta, and cosine of 2 theta equals cosine squared theta minus sine squared theta. So I am not going to give these to you on the verifying identities portion, although there have been years that I have done that. They can be involved, but we will not be looking at those. We are only going to use these whenever we need to for some solving trig equations. So one thing that's a little bit tricky about this is knowing when to use the double angle identity and when you actually don't even need to use the double angle identity. So we'll see that as we go. And actually, let me pull the unit circle up here so you guys might need your unit circle there. On Tuesday's test, you cannot use your unit circle, but I will give you a blank unit circle. I won't grade the unit circle, so like if you don't want to fill it in, you don't have to, but you will definitely need to be able to use it. Okay, so for our first equation, we've got to solve sine 2x minus 1 equals 0. So whenever I teach a new identity, a lot of times students' first inclination is just to automatically use it if they see the sine of 2x. We will use it sometimes, but we will not use it every time. If we did use this, so don't write this down because this is not going to get us anywhere. If I did make this 2 sine theta cosine theta minus 1 equals 0, can I factor that expression? Nothing I can pull out. I could move the 1 over to the other side and divide by 2, which would give me 1/2, but I cannot break this up and say sine theta equals 1/2 and cosine theta equals 1/2, because I can only do that whenever my expression equals 0. Right? I can't do that with the actual number. Because here I'd have to think about where is sine times cosine going to give me 1/2. And that's not necessarily the easiest to do. So this is a particular problem where we could apply that identity, but it's not going to get us anywhere. So let me show you what you do want to do for this problem. So now you would want to write this down. We want to actually treat it like 2x is just an x at the beginning, right? So we want to treat it like 2x is just an x. Don't treat it any differently than you would if it was not. So we just add 1 to both sides. So sine of 2x equals 1. So again, treat that like it's an x right there. What I want to do now, because sine is by itself, I want to figure out where does sine equal 1. If you're thinking of it, it's like you're doing sine inverse, because sine inverse means where does sine equal 1. So if I'm thinking about where sine equals 1, that happens at pi over 2. And it only tells us to look at principal values. I'll talk about in a minute what we need to do there, but so I'm going to just stop right here for right now. So instead of getting that x equals pi over 2, I'm going to get that 2x equals pi over 2. So now I can just very easily solve this. I could divide by 2, but then I've got complex fraction over here. What's the same as dividing by 2? What can I multiply that would be the same as dividing by 2? Multiply by 1/2, so I'm going to do that instead. Just makes it a little quicker to do the problem. Pi over 4. Now, whenever you find yourself doing a problem like this where you're dividing, like you have a 2x instead of an x, we probably want to look outside of the principal values. What it means is because we're dividing there at the end, our window that we look at needs to be twice as big. So rather than looking at negative pi over 2 to pi over 2, we would really want to look at negative pi to pi, which is the whole unit circle, right? Does sine equal 1 anywhere else on the unit circle? Not on the unit circle itself, right? It would be at 5 pi over 2, or we could add 2 pi again and get 9 pi over 2. But we really only need to look at an area twice as big as we were originally looking at, so we don't have to do that here. So this is going to be the only answer here. I'll show you in a minute where we will get more than one answer. Okay, we have a similar problem here where we've got tangent of 2x. I didn't even teach you the double angle identity for tangent. There is one, but we're not going to do it because you could figure it out just using the sine and cosine ones if you had to, and you're probably not going to have to. So we definitely don't need to use the identity here. I've got tangent of 2x minus the square root of x. So treat that 2x right there like it's just a single variable for right now. So we just need to move the square root of 3 over to the other side. So tangent of 2x equals the square root of 3. Now I got to think about where tangent equals square root of 3. And tangent's not on the unit circle. So I know that it's either at 30 or 60. I can't remember which one it is off the top of my head. So if I'm thinking of tangent of pi over 6 or 30 degrees, that would be sine 1/2 over cosine square root of 3 over 2, which would be 1/2 times 2 over root 3. The 2's could cancel here, but I'd get 1 over root 3. I need just the square root of 3, not 1 over root 3. So it's not pi over 6. If I do tangent of pi over 3, however, I will have square root of 3 over 2 over 1/2, which is going to be square root of 3 over 2 times 2 over 1. These will cancel. I will just get a square root of 3 here. So it's at pi over 3 for that. So what we're going to say here is that not that x equals pi over 3, but 2x is going to equal pi over 3. Right, and we're using 2x instead of x because we've got the 2x inside of the parentheses there. So to solve for that x, we just need to multiply both sides by 1/2. And so x is going to be pi over 6. Okay, now remember I said, like our last step on this problem is that we're dividing by 2. So it really means for principal values, we need to look at an area that's twice as big as what we normally would look at. Because when we divide it by 2, while it might not be a principal value, it might fit in the principal values after we divide by 2. So this is certainly an answer, right? But there might be more. So we got to think about, is there anywhere else that tangent is going to equal the square root of 3? It will not happen at 2 pi over 3 because you're going to get a negative square root of 3 there. It will not happen right here at 5 pi over 3 because you'll get a negative there. But right here at 4 pi over 3, I will have negative square root of 3 over 2 divided by negative 1/2, which will give me a positive square root of 3. Now, 4 pi over 3 is not really at the principal values are normally at negative pi over 2 less than x less than, I think it's or equal to pi over 2, right? So normally that's where we look at. But since I'm having to divide by 2, I really want to double that area. So if I double that, if I multiply this by 2, I'm looking from negative pi to pi. So in this 4 pi over 3 right here, instead of calling it 4 pi over 3, because that's too big, that's not between negative pi and pi, what could I call it? Negative 2 pi over 3. Okay? Because 2 pi over 3 here is this distance, but if I go in the clockwise direction, that distance, so negative 2 pi over 3. So if I say 2x equals negative 2 pi over 3, and I multiply both sides by 1/2, I'm going to get that x equals negative 2 pi over 6, which is going to reduce to negative pi over 3. Negative pi over 3 is between negative pi and pi, or negative pi over 2 and pi over 2. So this is also an answer. So let's make ourselves a note of what we're doing there. If you are dividing by 2 at the end of the problem, double the area of the unit circle. That you consider. Now, what is going to happen on these, if you don't do that last step, you're going to get one of the answers right. You will miss one of the others. It'll give you half credit whenever you do that. Now, on the first example, you actually could get away with not considering it at all because sine only equals 1 time on the whole unit circle. So it actually ends up working out. But for number 2, if you don't do that second step, you're going to miss that second answer. You're going to get the first one right, but you'll miss that second answer. Okay, 3 is a problem that we don't need to use any double angle identities or any double anything on here. So this is just sort of a review problem back from the other section. So let's see. Jackson, whenever you look at that one, what would you do first?
We already have negative 1 on one side. Do we want to move it to the other side?
Yes, we want everything on one side because we need this to be equal to 0. This looks like something we're probably going to have to factor. So we would need to move everything to one side. So,
+1.
yeah. Actually, hold on. That tangent's going to mess us up, isn't it? We do want to move, eventually you're going to move stuff to one side anyway, so let's go ahead and do it. It's not a bad move. And actually, I'm going to write this step. Alright, so let's put these in order, and I'm actually going to change the sign of everything so that I've got a positive 2 cosine squared x minus cosine tangent x minus 1 equals 0. That tangent is really giving us trouble here, right? Because I've got cosines, I could factor that stuff, but there's no way I can factor this that's going to give you a tangent in the middle, right? Maybe if there was like a tangent here on the end, I might get that, but I can't get this tangent in the middle. Any ideas of what we could do? What do you think, Hallie? Okay, let's do that. We can. So we've got cosine x tangent, let's change this, sine over cosine, sine x over cosine x minus 1 equals 0. Okay, so that gives us 2 cosine squared x minus sine x minus 1. Well, that's good because I don't have a tangent, but now I've got sine and cosine. Those don't match either. I can't factor this like it is. So what can I do now? Okay, I can change cosines into sines, right? So that cosine squared right there, I can change into 1 minus sine squared x. And then if I distribute that 2, I'll have 2 minus 2 sine squared x minus sine x minus 1. Let's combine the 2 and the 1, so I'll have, and let's put them in order, I'll have negative 2 sine squared x minus sine x plus 1. And again, we don't like having the square negative. We actually, I guess if I'd thought forward in my problem a little bit, I might not should have changed the signs here. It would have, now I'm having to change them back, but it's okay. So now I've got 2 sine squared x plus sine x minus 1. And now I can factor this, right? Because I'm going to treat it just like it's 2x squared plus x minus 1. All right, so I'm going to factor. We got 2 sine x and sine x here. And remember, when you got that number in front of your sine squared, you're going to have to sort of guess and check. There's no number you can multiply to get negative 1 that's going to give you the 1 sign in the middle. You've got to guess and check. So if you put the plus 1 right here and the minus 1 right here, then that's going to work, because whenever you check it, you'll get negative sine x, and you'll get 2 sine x, which when you put together gives you positive sine x. So that's right. So should have left more room on this problem. So we got 2 sine x minus 1 equals 0, and sine x plus 1 equals 0. So for that first one, 2 sine x equals 1, and sine x equals 1/2. Over here, sine x equals negative 1. This particular problem asks us to look at the entire unit circle, not just principal values. So we're looking for anywhere sine equals 1/2 on that unit circle. Bronwyn, where does sine equal 1/2? Pi over 6. Where else? Pi over 6. Good. So So there are two of our answers. We also want to know where sine x equals -1. So, Blaine, where does sine equal -1? Good, 3 pi over 2. Is there anywhere else for that one? There's not. 1 and -1 are the only numbers that are only going to show up one time on the unit circle for sine. Once for sine, once for cosine. Everything else should have two answers there. So, if you're looking at the whole unit circle. So there is our answer for that one. Questions? Okay, let's look at the fourth example. We've got 1 over cosine x minus sine x equals cosine x plus sine x. So, for this one, remember, we are not verifying identities. We are solving this equation. So, we can move things from side to side here. And are we going to have any luck solving something whenever we've got this cosine x minus sine x in the denominator? Can't solve for things that are in the denominator. How do we get stuff out of the denominator? Multiply. All right, so what we're going to do is we're going to multiply both of these by cosine x minus sine x, which on the left-hand side is just going to cancel. Over here, we've got cosine x minus sine x here. So we will distribute cosine x times cosine x is cosine squared x. Cosine x times negative sine, we would just write that minus sine x. Cosine x plus, here we'll get another sine x cosine x. You should notice those are going to cancel, so if you don't write that step at all, that's fine. And then minus sine squared x. So we got 1 equals cosine squared x minus sine squared x. Now, I could try to move the 1 over and try to factor, but is it going to factor cosine squared x minus sine squared x minus 1? We're not going to be able to get that sine squared in the middle. So you got a couple options for how you can do this problem. There's one that's going to take a little longer, and the other that's going to use those identities that we have up here at the top of this page. What does cosine squared theta minus sine squared theta equal? Cosine 2 theta. So we would have 1 equals cosine of 2 theta. So now all we really have to do, we're going to keep this, or I guess it's x in this problem. All we really have to do now is ask ourselves, where does cosine equal 1? Where does cosine equal 1? At 0. So we would say 2x equals 0, which would just mean x also equals 0. There's our answer. But remember I said if you're dividing by 2 for that last step, you need to double the area you're looking at. So we don't need to just look at 0 to 2 pi. We need to look 0 to 4 pi. So where else, 4 pi would be like going around the circle 2 whole times. Where else would cosine equal 1? What? Yes, 360, which since I'm using radians here, I'm going to call that 2 pi. And so if I divide by 2, there, x can also equal pi. And it would also equal 0 at 4 pi, but notice there's not an or equal to sign right there with the 4 pi, so you would not need to use it. So just 0 and pi would be your answers. Some of you may be thinking, I would have never recognized that, right? We haven't really used those identities yet. You may have never recognized this. You actually have another option on this particular problem because I think, oh, do you? Yeah, you do. You do have another option because you can do this. So this is like an alternate way of solving. So you pretty much have to do what I've done up to this point. But from here, instead, we could switch everything to sine or everything to cosine. So we could do cosine squared x minus 1 minus sine squared x. I'm sorry, cosine squared x. So that would be cosine squared x minus 1 plus cosine squared x, which would give us 2 cosine squared x minus 1. We could add our 1. So we get 2 equals 2 cosine squared x divided by 2. 1 equals cosine squared x. Square root both sides, so we would get plus or minus 1 equals cosine x. So we would look for where cosine equals positive or negative 1. That happens at x equals 0 and x equals pi. So you get those same answers if you do it that way. It takes a few more steps, but we're probably more familiar with this path, so some of you may choose to do that. All right, what questions do you have so far? Okay, now the last problem, you had a choice on whether or not you used the double angle identities. On example 5, there is no choice. You're going to have to use double angle identity. Because, unlike the first couple problems, I don't have cosine 2x equals just a number. I've got that it equals negative 1 minus 3 sine x. So I've got that sine x in there. So whenever you see that you have this double angle identity, but you also have other trig functions in the problem, not always, but usually you are going to need to replace this using that double angle identity. And up there at the top of the first page, it told us that cosine of 2x equals cosine squared x minus sine squared x. So let's replace that. Negative 1 minus 3 sine x is going to equal cosine squared x minus sine squared x. All right, Connor, have you got any ideas on what we should do next? We are going to need to move everything to one side and factor. Is it going to work well with a sine and a cosine? So should we change the cosine? All right, let's change the cosine. We know we want to change the cosine because over here we got just a single sine. It's not squared, so we can't change it to cosine. So, but this we can change to sine. So you could move everything first, or you can do this first. Let's go ahead and do 1 minus sine squared x minus sine squared x. And then if we combine the negative sine squared x and the negative sine squared x, what do we get? What? Negative 2 sine squared x. So we'll get 1 minus 2 sine squared x. So I would do that first before I move everything. Now let's move everything like Connor said to do. So I'm going to add this 2 sine squared x over here and subtract this 1. So I will get 2 sine squared x. I'm going to put this minus 3 sine x here so my terms are in order, and I'll have minus 2. 0. Okay, at this point you can factor. So you'll have 2 sine x and sine x. And we need to multiply to get -2, which means we need a 1 and -2. So we'll have a +1 here, a -2 here. If we check to make sure that works, that gives us sine x here and -4 sine x, which does give us the -3 sine x that we need in the middle there. So we factored it correctly. That part you can do in your head. Don't have to write down necessarily. So we will set each one of these equal to 0. We'll get 2 sine x plus 1 equals 0, and sine x minus 2 equals 0. So here we'll get 2 sine x equals -1, and sine x equals -1/2. Here we get sine x equals 2. Does sine ever equal 2? It does not. What's the highest sine ever is? 1. What's the lowest it ever goes? -1. So if you get anything outside of that range, then you are not going to get an answer from that. But we do need to know where sine equals -1/2. And so, Noelle, if we look at the unit circle, where does sine equal -1/2? 11 pi over 6. But for principal values for sine, it is -pi over 2 less than x less than or equal to pi over 2. So sine x equals -1/2 right here at 11 pi over 6, but that's not between -pi over 2 and pi over 2. So what would we call it instead? -pi over 6. So x is going to equal -pi over 6. Okay, 6 is going to be similar. I want you guys to try 6 here. So try number 6 on your own. We're not going